Solutions can have a variety of quantities of solute dissolved in a solvent. Just really anything that's possible, except past our saturation point. And so we need a way to track this and communicate it. And we use this idea of concentration in chemistry to do that. So concentration is just the measure of the amount of solute and the amount of solvent that is in a solution. There's a lot of different ways to represent it, but they all kind of come down to a ratio of solute over the amount of the total solution. We have a few different styles of measuring concentration that'll actually be a ratio of solute over the amount of solvent, which I don't think we'll actually discuss today. So I'm going to go through some of the common ones that you probably already are aware of in your daily life and the ones that we use in chemistry, and then focus in on the concentration used to track the amount of cannabinoids in cannabis. So first I'm going to start with the chemist's favorite version because it's my favorite, and it's molarity, and it is abbreviated capital M. And this is the moles of the solute divided by the volume of the solution. And specifically, we make sure the volume is in units of liters. And this really tells a chemist the number of molecules that we have in that 1 liter of our solution. And this is important to us because the way chemical reactions occur is 2 molecules need to collide, and then they're able to, if they have enough energy, change the bonding structure before they bounce off each other. And so the number of particles is really key to predicting the amount of a product that would form in a chemical reaction. And this is why we track concentration as a counting number of molecules. And that's what this moles really is. So moles is really a counting number. And it stands like a dozen, right? A dozen stands for 12 things, and it could be anything. A mole is a number of anything, and we usually refer to molecules or atoms with it because it's a really big number at 6.02 times 10 to the 23rd things. So it's a way for us to say, we have so many molecules in this like small glass of water, but we have maybe only 0.5 moles. So it's a way to simplify and to use smaller numbers as we track the number of particles. So here's an example of how you could see molarity used. You might see a solution labeled as 0.5 molar sodium chloride, and it would be aqueous. And so this 0.5 molar means 0.5 moles of our solute, which will always kind of give the concentration in reference to the solute molecule. So it'll be moles of sodium chloride, which is a table salt, in 1 liter of solution. And the solution is going to be a solute of sodium chloride and a solvent of water. And we can use this information to then say, if I have a solution of this concentration, if I take a small amount of it, I can calculate the exact number of sodium and chloride ions that would be in that solution. Another common way to represent concentration is to show the amount of the solute in either its mass or its volume, if it's a solid or a liquid, and make that a fraction or a ratio with the total volume of the solution, and then multiply that by 100 to create a percentage. And so we typically see weight per volume percentages as solutions where we have a solid dissolved like a salt. So I would say a 5% sodium chloride solution, because sodium chloride would be a solid when it isn't actually in the solution. So we oftentimes see these weight per volume percentages in hospital settings. So a lot of IV solutions are salts dissolved in water. And so it's tracked as the mass of the salt dissolved in the total volume of the solution, which is the salt plus the water. And so something like a 0.09% solution of sodium chloride might be an IV that you would get if you were dehydrated at the hospital, something like that. So then volume per volume percent is when we have a liquid dissolved in another liquid. And in these cases, we usually have the solute would be a liquid on its own. So a great example is ethanol or alcohol. And when it's mixed with water, the ethanol or alcohol is the solute and the water is the solvent. You'll have more of it around. And so you would have, let's say, 40 milliliters of ethanol dissolved in enough water to make a 100 milliliter solution. And that would be a 40% overall ethanol solution. So that would be something like that you would find in vodka or another hard liquor. And so we tend to track the most common place that I've seen these volume per volume percentages is with alcohols that you would like purchase, or like isopropanol that you would keep in your first aid kit is another one that you might see, or the percentage of acetic acid that you would have in household vinegar at home, like those jugs of white vinegar. So let's take a look at that example of acetic acid. So if I read a label on my vinegar at home, it says 5% acetic acid. And so this really means that I have 5 milliliters of acetic acid in every 100 milliliters of solution. And remember that solution, that means the acetic acid plus the solvent, which would be water. And this would all be times 100 to make it a percentage. And so we typically have different types of units that work for this, for volume. It could be milliliters or it could be liters. But the important thing is that the units are the same for the solute and the solvent. So that way, when we get a ratio, we actually calculate a number that doesn't even have any units associated with it. So for molarity, it was really important that we have our units of liters for our volume. And here, the only thing that's really important for our volume to volume percentages is that the units are the same. For our weight per volume up above, we typically use grams for the mass and milliliters for the volume, especially if you don't see any units written, then you can assume it's grams and milliliters. So cannabinoid compound concentration in plant material or in a concentrate material is usually represented as a percentage. And these are mass to mass percentages. Oh. I noticed a typo. These are mass to mass percentages. And so what we're seeing when we see a percent on a label is the mass of a cannabinoid, like THC, divided by the mass of the dried plant material. Now, the percentage is calculated with the mass of the cannabinoid in grams and the mass of the plant material in grams as well. The units have to be the same in the calculation for the units to cancel. And then it's always times 100 to create that percentage. But most of the time when we track the amount of a cannabinoid, it is going to be in units of milligrams. So if you like have a gummy, usually they're 5 milligram or 10 milligram dosages in something that's like an edible. And so cannabinoids, you don't need grams of it to have an effect from it. And so there's a little bit of a a disjoint there in that we think in milligrams for THC, but our percentages are really being represented as a ratio of grams. And so it's easy to get confused about what that percentage can actually mean. So we're going to break it down here in an example. So if you are looking at just like cannabis flower dried, it typically contains about 15 to 25% THC. Concentrates can have up to like 90% THC in the fluid in like a cartridge or in a shatter or another type of like method of delivery. But let's just take a look at just like a cannabis flower, and this might be something that would have like a label that said 17%, right? So what this percentage is saying, so 15% THC is really equal to 0.150 grams of THC in 1 gram of dry flower times 100. That 1.150 gram right here, this is equivalent to 150 milligrams. So it's saying in a gram of the flower, there's 150 milligrams of THC. And so if I just calculate this by 0.15 divided by 1 is 0.15 times 100 is 15. That's where I'm getting that percentage. The 0.15 grams is really coming from, it's just in a different color. So it's a conversion from milligrams to grams. And so 1,000 milligrams equals 1 gram. So I can convert back and forth between the two using dimensional analysis. If I know the number of milligrams, I would say something like 150 milligrams times 1 gram divided by 1,000 milligrams would help me convert. So 150 milligrams divided by 1,000 would equal my 0.150 grams, or my 0.15 grams times 1,000 will equal my 150 milligrams. So I can convert in between these two. And so we're going to think about how many cannabinoids are in a dose or in an amount of material in milligrams, but we're going to write that percentage in terms of a ratio of grams. So once again, cannabis flower, if it is 15 to 25% THC, that means 150 to 250 milligrams of THC is in each gram, 1 gram of flower. Looking at a label, so here is some dried flower. Let's see what it says. So for this one, it says the THC is 0.5%, but THCA is 26%. So this means in 1 gram of the flower, and this is Old Man Lemons, we're going to have 5 milligrams of THC and 260 milligrams of THCA. Now it looks like this is a 1/8 ounce, which is going to be a little bit more than 3 grams. But if this is 1/8, then that is 3.5 grams of flour. And so we can multiply these by 3.5 to know the total amount of THC and THCA contained in this baggie. And so 5 milligrams times 3.5 is going to be 17.5 milligrams of THC. And then our 260 milligrams for THCA, times that by 3.5, and you're going to get 910 milligrams of THCA. And that's in the entire package. And so that THC quantity seems really low, right? And that is, it's very specific that both the THC and the THCA content is being reported here, because we'll talk about this in a later part of the quarter. The decarboxylation of THCA produces THC, and that process can occur just by heating the material below its vaporization point. And so we have this, as this is heated, it will decarboxylate the THCA and produce THC. So that amount of THCA is the maximum amount plus the amount that's already THC that is accessible to be ingested as THC and have a THC effect. Now, of course, it doesn't mean that absolutely all of that is going to end up in a bloodstream when consumed. So like if we were looking at the 1 gram of flower, if 100 or 1 gram of flower was smoked or ingested or vaporized, we wouldn't see exactly 260 milligrams of the THCA instantly converted into THC and then completely absorbed by the blood. There is a large decrease, and depending on how it's ingested, you only get a certain percentage of that actually getting into your bloodstream. And even then also there is some loss of THC conversion into THCA converting into THCA. But it's helpful to know that it's basically about 26.5% of possible available THC in 1 gram.